Good morning. We're Team 8. My name is William Billini.
Xavier, Bercy, and I'm Ricardo, Charlestin.
And our project is a digital photolithography system. So here's our topic selection. Our problem statement is to innovate the process of creating screen printing frames. As you can see pictured here on the right, these are the different components of screen printing frames, which is a manufacturing process of transferring images with ink onto products. What we want to do is eliminate the requirement to print polyester film and print an image directly onto the film, which is required to transfer the image onto the screen. So our objective is to design a digital photolithography system with motion control and machine vision. Here's our system. So our motivation is to eliminate consumables like the film, boost productivity, and improve image quality. So what is photolithography? Photolithography is the process of transferring images or patterns via optical methods onto photoresistive materials. The spectral range which we are using is between 350 to 420 nanometers, which is UV light. This image shows the technology which we're using, which is a DLP chip from Texas Instruments. It's a micro-electromechanical system with thousands of microscopic mirrors. As the light is shown onto it, it is projected through a projection lens onto the photoresistive material. This is how printed circuit boards are manufactured. So here we have a table of some of the standards that we observe for welding steel, fastening hardware components to the frame, determining the proper wire gauge for the electronic enclosure, and operation of the stepper motors.
All right. The design for our prototype is made up in the three major components: the light engine, the motion control, and the machine vision. The alternate design that we have for the light engine utilize a FPGA-based DMD driver.
Yeah.
And it also has a liquid-based heat exchanger and use a metal overlight lamp. And the design that we use for the light engine for our prototype is a DLP Lightcraft 4500 from Texas Instruments. And the reason why we went ahead and picked this light engine is because it was donated to us. And we only had to make like a modification where we switched the original lamp that came with it and replaced it by a UV LED from Luminous. It goes by the name of CPM40 UV. And the alternate design we had for our motion control is a 2200 series conveyor belt from Dollar, which is also an expensive one. But we went ahead and proceeded with an XY table with extruded aluminum powered by two NEMA 70 stepper motors, and which operate in a similar way to a CNC roller. And for our machine vision, we stick with the same plan as we planned initially, which is a USB webcam that programs and algorithms generated in MATLAB. For our structural design, which is an enclosed design with access doors, just for safety reasons, and it is a welded steel frame that is enwrapped with steel sheet metal panels. And for simulation, we did our kinematic analysis where we were able to show the path, how the light engine will follow a serpentine pattern related to the XY table as it is moving on top of the frames. And then we went ahead and do the stress analysis on the board that is holding the light engine. In the worst case scenario, we assume that the light engine is 5 pounds, which in reality it weighs less than that, less than 2 pounds. And we were able to obtain a maximum stress analysis of 3 megapascal. And again, we found a factor of safety to be 8.5. And for the construction process, we started first of all by welding the structural frame. We fastened the sheet panels, attached those to the frame. We mounted the XY table to the frame. We'll build the electrical enclosure, as shown in the picture right here, but without the beagle bone. And we mounted a USB webcam on top of the board, and we installed a UV LED in the light engine, which is the modification that we made. And the picture on top is Xavier and the beginning process of welding the steel frame.
All right, so now I'm going to talk about the experiments and results. So the very first test that we did was we wanted to determine what is the output power from the light engine with the UV LED. The photoresistive material requires radiation of UV at 380 nanometers at 12 milliwatts per centimeter squared. So it was important for us to determine what is the actual output after we installed the LED. So what we did is we set up the light engine in front of a fiber optic optical detector at a distance of 10 centimeters. And we conducted 4 trials where we were measuring the output power in intervals of 30 seconds. So here are the results. The first thing that I need to state is that the highest output power that we recorded was 5 microwatts. And I do need to state that this experiment was conducted in a dark room. The other thing that is noteworthy is that the power decreased over time. And that is because as the LED warmed up, its output power decreased. That was expected as it is stated in the data sheet. So what about this 5 microwatts? What will that do for us? The required material requires 12 milliwatts. At 5 microwatts, that would take over 40 minutes to expose. But then after the experiment, we found out that the photodetector is calibrated for 400 nanometers. Thus, our 385 nanometer LED was out of its range. So what we suspect, which was actually recorded or detected by the optical detector, are harmonic frequencies emitted by the optical engine. So our next test, we just wanted to see if it'll work, if it can expose an image onto the photoresist. So what we did is we constructed a bunch of wooden frames measuring 6 by 3 inches, and we stretched this screen printing mesh and we stapled it onto that. Afterwards, we applied the photoresistive material. So we did 4 tests. I first did 2, measuring at 5 minutes, and we projected a checkerboard pattern. Then another one at 3 minutes, and then another one at 90 seconds. After exposure, they were rinsed in the bathtub so that the non-polymerized emulsion would just rinse away. So we were able to obtain fairly satisfactory results at 5 minutes and also at 3 minutes. However, at 90 seconds, it was underexposed. So that means that what this entire experiment proves is that the light engine is emitting UV radiation with sufficient power to polymerize the photoresist. So our next experiment is on the machine vision system. All these experiments were done within MATLAB. So what we did is we placed these 3 frames on a flat surface. So this is where you're supposed to load them, and the camera's mounted up here. So what happens is inside of MATLAB, it takes an image, it imports it, and then processes the image. So what you can see here is that it found the profile of each of these frames, and also inside of the code, it detects the centroid and orientation of each frame relative to the edge of the image. This image over here is what we're calling the test image. We created this in an image processing software. And the goal was to take this image, import it, place it on the center of each frame, and properly orient it to each frame, as you can see here. So overall, this experiment proved to be very successful. So now I want to talk about the economic analysis. I know this is a lot to look at, so I'm just going to run through it quickly. We provided a theoretical business case of a local screen printing shop of having to create 45,000 of these per year. So we went to a local screen printing shop and we were able to obtain times for the actual time to print the film, cut the images out of each film by hand with scissors, and then to expose the frames using conventional screen exposure systems. So it turned out to be about 22,000 hours, and at the rate of $10 an hour, you're talking about over $200,000 in labor expenses. Now we're going to talk about material expenses. So we needed to determine how much film is required to print 45,000 of these frames. So we figured out that it would take 28 rolls of film, and at the cost of $119 per roll of film, which is 100 feet long by 2 feet wide, you're talking about an annual cost of over $3,300. Finally, we all know that inkjet ink is very expensive. So at the rate of consuming 1.5 cartridges per week over a year, at the cost of $145 each, you're talking about over $11,000 in expenses. So what does this all turn out to be? The first year alone, you're talking about $236,000. So what we did is we did a proper engineering economic analysis over 7 years, over the system's lifetime, and we increased the labor costs 4% every year, and also the material expenses 2% every year. So after we get these bottom line annual costs right here, we then put it into our cash flow analysis, which takes into account depreciation and the taxes that you would have to pay on this additional profit. So what we determined for a theoretical system that costs $150,000, in the first year alone, their net after-tax cash flow is $150,000. That means that for this system, the return on investment is 1 year.
This is our project timeline. We started in mid-September in April, March, April. We came up with 3 global perspective for our project. We have the safety standards, a multilingual manual which was translated in English, French, and Spanish, and an electrical compatibility that was taken into account for a switch power supply. In conclusion, we came up with a multidisciplinary system, which included mechanical engineering, electrical and computer engineering, and industrial engineering. And the objective was to create a digital photolithographic system to innovate process of creating printing frames, the light engine to prove successful and exposing frame, and a machine vision algorithm were successful. For future work, there is a market demand for small desktop system, and there exists an opportunity for the scheduled jobs from a company called IAB with improvement optic line with less than 40 micrometer can be achieved. And thank you.
Thank you.
Comments? Yes.
Well, the first question I have to ask is, why is your box reflective on the inside?
We really didn't take into consideration. The light engine is supposed to be facing downwards. And also, the thing with UV radiation is that its power decreases over distance. So any UV radiation which is reflected on the inside of this case would be negligible by the time that it is reflected off of the surface and then back to the photoresist. But for this prototype, we just used inexpensive sheet metal panels. We weren't able to actually install the light engine and to have it move in the serpentine manner.
Okay, where is your light engine?
The light engine is sitting outside on top.
Gotcha, and where would it have been mounted on that system?
It would have been mounted on this crossbar.
And that is 10 centimeters from screens?
No, it would be mounted, the projection lens would be mounted 10 centimeters from the surface of the screen. And the only reason we figured out 10 centimeters is because we were limited by the actual projection optics that are included in that light engine. So what we did is we projected a fine line grid pattern, and we played around with the focus to see what is the smallest image. Because in the end, we want to fit an entire image onto here, so 10 centimeters.
And why isn't your camera mounted?
The camera is mounted, it's right here.
The light source?
Because of difficulties in programming it, what we did is when we created the image, when we created this image, what we had to do is we had to chop up the image in matrices measuring like 900 by 1100 pixels, right? And so each matrix indexed over 10 pixels, right? And so what we wanted to do was create a series of images to create a movie, right? As the light engine is scanning over, right, the frames are changing. We were having trouble getting it to do that. We managed to make the images, but we were having problems with the LED flickering, and it's just very difficult to program. Also, we got it at the end of February. It took us 7 months to lobby Texas Instruments to donate it, so. Yes, Dr.
Just a
Basil.
quick question. Why, of the 3 tests that I see at the bottom, is the middle one flipped over?
What do you mean flipped over?
Different direction.
Oh, this one. Okay, so that's a good question. So
I wouldn't be too happy.
basically, what's happening is when we're modifying this, we're saying, okay, place the center of this image at this coordinate, and then rotate it. So it is really a matter of what is happening here. So this one, it could say that the angle is 95 degrees, and then this one, it could be like 265 degrees. So that's why I rotated.
Was that on purpose, or did that just happen?
It just happened, but it doesn't really do anything.
I would strongly disagree with that. If you're printing a T-shirt and you print it upside down,
It's not upside down, it's just rotated. See, T-E-S-T.
well, I mean,
But no, because
Semantics,
these are
right?
rectangular.
Semantics, right?
But these
But
are
yeah.
rectangular objects.
Sure.
So it doesn't matter when they come out. You just flip it upside down and put it on the machine. But that is something.
No, because it's oriented. Anyway, it's fine.
No, look, it's
yeah.
a rectangular object.
But it's
and there it
mirrored,
goes.
right? It's
in the
mirrored.
center.
It's
So
mirrored.
you can take this guy and this guy and then rotate them.
It's mirrored, though, right? Isn't it?
It is not.
Okay.
T-E-S-T, T-E-S-T, T-E-S-T.
I guess the problem is, what if you're printing on a material that is not
Right.
symmetric and has an actual orientation where you need to have certain orientation? I mean,
So-
in this case, you have
Yeah, that's a good
rectangles,
question. So
but you
what
have
you
a
would
shared.
do is you would take the frame and place it on the machine. And then if there is an orientation problem, you could adjust it on the machine by loosening it, rotating a
Yeah.
little bit. But I assure you, this would not affect
Okay.
the final exposure.
Okay.
I have 10 years experience in the screen printing industry.
10
It's
years.
not a big problem.
So I'll follow up.
Sure.
What do you think your major accomplishments were from this project?
Actually exposing the frames. actually exposing the frames. These guys did a wonderful job building the entire thing. They built the whole thing. I was doing all the experimentation and all the programming. And just having it work, you know, doing this machine vision algorithm, we're very satisfied.
You feel like you accomplished your main objective?
No, the main objective was to have a step and scan, like a step and scan system, right? So what you see here in our kinematic analysis, we did an animation. So what was supposed to happen is here's the light engine,
Yeah.
moves across,
Yeah.
and then it advances forward and it does the same thing in a serpentine manner. We did not accomplish that.